I gave the definition of a vertex algebra, but it's a funny kind of algebra in some sense. It's a vector space, and then we have some object called the vacuum vector, which behaves something like a unit. There's this object T, and most of the structure is in this collection of fields. And somehow you think of this collection of fields as, so like in the example that we had last time, contain one field, or maybe two fields if you include the unit. And then from there you start producing normally ordered products and things like this. So it's a bit peculiar if you think of an algebra as being like a Lie algebra, say, a vector space with a product defined on the vector space that goes from V, tensor V to V. So the first thing I want to do today is explain that there is a way of thinking about vertex algebras that's much more in line with that intuition as algebras in the sense of a vector space with some products. And this is basically what's called the state field correspondence. And then after that, I want to go to the next example, which is so-called lattice vertex algebras. Okay, so let V be a vertex algebra in this sense. So the first thing I want to do is introduce some additional spaces of fields. So let if tilde, if bar, and if prime Okay, so this is some very large space of quantum fields. The only condition that we put on them is that they commute with T in this way. So this next collection, F bar, depends on the original set F for its definition. It's the set of all quantum fields that form local pairs with all elements in F. And the third one is going to be also produced from F in a certain way, but it's going to be in some sense generated by F. So we start from F and then form all derivatives, all nth products, and iterate this construction, and we call this F prime. Okay? So now I come to a key lemma. Put this down. So I'm going to refer to this as Dong's lemma, because that's how I learned it. But I've since learned that perhaps the attribution is more complicated, so I'm not sure. Lee might be involved in this. But anyway, the statement of the lemma is that if you have three mutually local quantum fields, and you take the nth product of two of them for any n, recall the nth product of fields was defined in the previous lecture, then again, this new quantum field and our other quantum field also form a local pair. Okay? And I won't give the proof of the lemma, but using the lemma, we have the following statement. So we have if okay. So this containment here is by definition, right? If line, all quantum fields, I guess I should have said NF tilde. And the first containment is also clear because we began with F and then just started forming nth products. And the middle containment is a consequence of Dong's lemma, right? Because it says if you start with a collection of fields that are mutually local and you start forming nth products, all of the resulting pairs are going to be mutually local. Okay? Okay, so now I'll give a sort of structural theorem. So the first part of this is actually what was a question at the end of last lecture. It says that if you take any field and you apply it to the vacuum, the result has no polar terms. Okay. So what we'll do, in fact, is to define this assignment from A to V, give this a name. So let me call that S. Okay, now the second part of the theorem is a property of S. It says that if we take the nth product of two fields, then S of the nth product is given by, well, the nth product of S of B. But here, note, this nth product means the z to the minus n minus 1 coefficient of the field A of z. So this is the first indication of a link between, or some sort of correspondence between V itself and the set of fields on V that intertwines this operation of nth product in fields and the individual coefficients of the fields in V itself. This has become increasingly explicit as I state the theorem. Okay. And the third part, which I think actually is given the name Goddard's uniqueness theorem, which will sort of be crucial in proving, well, ultimately we're going to see this S is going to be an isomorphism between the set of fields and the vector space. And we use that to transfer this nth product from fields to structure on V. Yeah, and so this is saying, well, if we take any sufficiently large collection of quantum fields on V, where large means its image under this map S is all of V, then if we have any other element which is local with that entire set, then somehow this map S is injective on it. If it maps it to 0, then the field must have actually been 0.
So in this last statement, SE is any quantum field or is it
It's local. I think it's any element of F tilde, but we'll see during the proof, I guess. Okay, so firstly, let's write V of Z in place of A of Z applied to the vacuum. And then if we take the derivative of this, well, we can rewrite that in terms of A. So we get commutated with T. But we know that T annihilates the vacuum, so this is just T applied to this. So this is equal to T V of Z. A of Z? Yeah, that's what he asked as well. I believe so. Yeah, well, F tilde is the biggest of these spaces, so certainly it's not going to be any more general than F tilde. Yeah, I thought the question was maybe it was only defined for, say, F prime or something, but it's for F tilde. so we get the simple relation between different coefficients of v. So basically, if you had any non-trivial coefficient Vn where n is negative, then you would find that the next most negative coefficient would also be non-zero, and so on and so forth, down to negative infinity. Since Az is a quantum field, that can't happen, so really the lowest term is actually 0. And similarly, this relation tells you, well, if you know what V0 is, then you know what V1, V2, etc. are, and are given by the formula. So that V0 called V, and that's that. So for the second part, we start with the definition of this nth product. And of course, what we're supposed to do is apply it to 0 and see what happens. So the residue in Z. Here's 0. And the first key observation is the second term vanishes, right? Because here we have an expansion of some function in positive powers of z. As we saw in the first part, a of z applied to the vacuum also only contains positive powers of z. And the residue is asking us to take the z to the power minus 1 coefficient. That part equals 0. Okay, so now we get something which only has positive powers of w, and when we apply s, we're supposed to take, well, basically set w equal to 0, right? Okay, but if we do that, then this part just becomes s of bw by definition. This part becomes simply z to the power of n. So we get residue z to the n And extracting this coefficient gives us exactly A sub n. Yeah, it's a bit of a funny notational issue here, right? To write the field, I have to choose a variable, but, you know, S is just an element of V. Okay, and for the third part, now we're going to use locality. So what do we have to prove? So we've got set G. So let B be some element in G, and we have A, which is local with it. So So this equality, and I'll apply both sides to the vacuum as before. And now the right-hand side, well, or rather on the right-hand side, I'll use part 1 to rewrite this term as e to the, I forgot to write it explicitly, but, well, this clearly is the exponential of z times t applied to this element v, right? And what is it that we're assuming? We're assuming that S of AZ is equal to 0, right? So right-hand side equals 0. So now, let's put W equal to 0 here. So we get Z to the N times S of B equal to 0, right? But this is valid for, well, so firstly, if this thing is 0, then I can cancel the Z to the N. That's not going to change anything. And this is supposed to be true for any element in G, but we know that S of G equals V. So the field A of Z actually was 0. So the corollary is that if we look at the restriction of S, which is defined here, to F prime, this is not yet a corollary. So the restriction of S to F prime is surjective. Why is that? That was one of the axioms of the vertex algebra, right? So the axiom is that if you start with the vacuum and then you just apply all of these modes or coefficients of fields, you eventually get the entire vertex algebra. So this is surjective. And the corollary of this theorem here is that the restriction to F bar is injective, right? Okay, so we have an equality of these two sets of fields. And this map S is an isomorphism to V. So we give a name to its inverse. We call it Y. Well, actually, these two statements, I'm going to call them 1 and 2 of this corollary. 3. Now, the consequence of the second part of the theorem says that this map Y, so this is now the so-called state field correspondence, and it intertwines nth products in the vertex algebra with nth products of fields. Okay, so that's the moral, is that this, the structure of vertex algebra is a lot more rigid than it appeared at first. It's not just some you can define it as some collection of fields that have this locality property. But if you assume sort of a small amount of additional structure, you're basically forced to have this picture where, well, you can think of the vertex algebra as being a vector space equipped with a bunch of products. So it's by some conditions. So what conditions exactly? I mean, conditions or axioms on these products that I'm talking about are all contained somehow in this nth product identity. So as a first step towards that, I'll give an exercise, which is to prove the so-called Borcherd's identity. Okay. So it's not too difficult, but I'll give a hint to get started. Okay, so we had this notion of, well, a local pair, but more generally a local formal distribution. So if you have some operator-valued series in Z and W, you have this notion of it being local if some sufficiently high power of Z minus W annihilates it. So left-hand side is local. The question is why. Secondly, so you apply the theorem that we saw in the first lecture, and then for the last step, use the state field correspondence. Okay, so what I want to do next is kind of go towards using this machinery to actually do computations in vertex algebras. But there's kind of a lot that I have to get across rather quickly, so I'm going to do most of it in the form of exercises. So the first one is... right. Yeah. Well. introduce a new notation. It's called lambda bracket. So lambda bracket is just a convenient way of describing denoting the OPE that we had in the first lecture. So what I mean is you take these jth products for j positive between our two elements. Remember, normally, well, if instead of elements of V, so the way I phrased in the first lecture was in terms of fields rather than elements of V. But of course, now we know that it's the same thing. There's an isomorphism between V and the set of local set of fields. So instead of writing fields, I'll just write elements of V. The jth product of the fields corresponds to the jth product of elements. And instead of the delta function, I'm just going to put a formal variable, lambda to the j. So it's just a generating function for these positive products. For those who like generating functionology, one can write this as a residue with an exponential here. Okay? We call this the operator product expansion, or OPE. The exercise basically to deduce some basic properties of this OPE. Well, the next property has nothing to do with the OPE, but whatever. Deserves a new line. So I won't ask to prove these two, as they're a little more difficult. Well, no, actually, I will exercise. Okay, so you can pretty easily deduce this non-commutative Wick formula, as you see in the exercise. So the first thing to do is to apply this operation, which kind of defined the lambda bracket in some sense, to this relation that we proved in the last lecture. Show that you get this form, and then play with that a bit and deduce this non-commutative Wick formula. Okay, so I'm sorry for throwing so many formulas on the board so quickly. The point is, firstly, that they're all true, but secondly, that once you have these formulas, you can start computing OPEs of pretty much arbitrary elements in your vertex algebra. So to illustrate this, I want to do an example, return to this example of the Heisenberg vertex algebra, and deduce some interesting non-trivial consequence from this. So returning to H, let's call little h the element of the field H. So its lambda bracket is just lambda. So more correctly, I should probably write something like vacuum here, right? But I'm probably just going to omit the vacuum. Okay. So recall that this other field, L, that we had was 1/2 of the normally ordered product of H with itself. Okay? So exercise. can use the rules to compute the OPE between L and this element H, and we get TH plus lambda H. Now we can go further. So how would you do it? You would write, L is by definition this here, this normally ordered product. So you've got a normally ordered product here. Sorry?
It's easier to do H lambda L.
It's true. But, yeah. The point is, so we've got this formula that gives us, tells us what to do if there's a normally ordered product in the second term. Well, then we should use skew symmetry to swap the two terms, then use non-commutative Wick formula, or do it in the other order. Okay. Then next prove that L lambda L is T plus 2 lambda L plus lambda cubed over 12. Again, just by using these formulas. So if you take that relation and kind of open everything up and go back to the original definition, see what you get the following thing. Okay, so you recall right at the beginning of the first lecture, we had these operators D, M. Did I call them D? Yeah, D, M, that satisfied the relation without this extra term here, right? Then, well, in order to make D0 well-defined, we had to introduce normal ordering. And then we introduced this whole theory of OPEs and normal ordering, the interaction, which is finally summarized in this set of formulas that I've given here. Then we're able to compute the commutation relations between these newly defined L's. And somehow this remarkable extra term appeared, which, for those who know, is an example of a Lie algebra 2 cocycle. So it's, there's a unique up to scaling 2 cocycle on this Witt algebra. And somehow the lesson is by breaking the definition of D in order to make it well-defined, what we got back was a representation on the space H, not of the Lie algebra D, but of this central extension of the Lie algebra, which, by the way, is called the Virasoro algebra. Okay, so just throwing some keyword, sort of buzzwords there. Okay. Any questions? So another thing that I can do now that was completely unclear in the first lecture is define module. Well, actually, before that, let me do one more thing. So something we can do is take b to be L plus some constant times the derivative of h. And the exercise is to compute the OPE of this element. We find that we get more or less the same thing as in the case of the Virasoro element L, except that now we get this funny factor here. Now I can define a module over a vertex algebra. There's a vector space M together with for every element in V, a quantum field, but now on the vector space M. And the vacuum vector should act as the identity on M. And if I take the nth products of two guys, then this should act as the nth product of the fields associated to A and B. Okay. So V itself in particular is a V module. An exercise to deduce another what should seem like a desirable property of this assignment. In fact, you can deduce it from these axioms here. And just to give an example, well, that's the tricky thing, right? So it's not, a priori it's not clear what T acting on M should be, right? But what we do have is this relation.
So you don't ever have to be T-mod, C of T-mod?
Not yet. Yeah, well at this point, no. Yeah. So an example of non-trivial V module, for, well, V, the only vertex algebra that we have so far, H, we take one of these other modules for the oscillator algebra, then it turns out that this can be easily given the structure of a module over V. Yeah?
So unfortunately, in the literature, there's like probably 1,000 different definitions of things that are called modules with a lot of adjectives, like weak, weakly, strong, fine, whatever they are.
Yeah.
Experts don't know them. I myself don't know anything. So these modules are called what typically? Or there's not even consensus of what these are.
Well, I guess there's not consensus because they're called by me module. And yeah, I mean, right. So what tends to happen in the literature is that module without adjectives means already a bunch of nice properties like maybe finite dimensional weight spaces, conformal, as you said, bounded below perhaps, things like this. And they say, well, you know, a module that doesn't satisfy all those properties we'll call like a admissible module, or if it's even weaker, we'll call it a generalized module, blah, blah, blah. And when you reach this level of generality, it's called, you know, there's like 5 adjectives, blah, blah, module. But I don't know. Yeah, I'd do it the other way around, I guess, and call this a module, and then if I want to impose conditions, then say so. But yeah, it's a good point. There's, in the literature, there's a lot of fine gradations between different properties that you want your modules to satisfy, and what some person calls a module without adjectives might well be a module in this sense with a bunch of extra conditions.
So there are interesting modules which are not conformal without the
Well, I don't know.
Take a vertex algebra without a solve.
Depends whether you find that interesting. So in this particular case, so we have to say what the, well, in particular, we have to say what the field associated with H is going to be. And it's kind of going to be the only thing that you can define it to be, Hn, which, remember, already acts on kind of H is more or less the same, H mu is more or less the same thing as H. The only thing that's different is that this mode H sub 0 acts by the constant mu instead of 0. So really, if you identify H mu with H in the natural way, then this is just H of Z plus mu Z inverse. Okay? So let me remark, checking that this thing is a module in the sense that I've defined it is not entirely obvious, or rather, yeah, that it is a module is not entirely obvious, and checking that it is not entirely trivial. But I'm not going to comment more on this today. If there's time, I'll comment on it at the end of the 3rd lecture. Okay. So now I'm way behind schedule, because now the other half of the lecture was supposed to be the construction of so-called lattice vertex algebras.
This module is H0 is central in this algebra, isn't it?
Yeah.
And it's a split central extension. So just take a one-dimensional representation of the whole thing and tensor it.
Maybe it is obvious then. Yeah. Okay. I guess the point I want to make more is that in general, this issue, yeah, I guess the confusion that I want to guard against is the following thing. So with this initial definition of a vertex algebra, we say you have a vector space, you have a bunch of fields, and they're pairwise local. So you could say, well, maybe we'll just define a module to be some other vector space, and you know, for each element in our vertex algebra, we just assign some field, quantum field, and these should all be local as well. But this is not the right thing to do, because that's like defining a module for a commutative algebra as saying, well, you just assign an endomorphism to every element in your algebra completely randomly, and the only thing you require is that they commute with each other. But that's not enough. You have to require also that the product in your algebra gets taken to the commutator, or you know, depending on what, you know, gets taken to the product of operators in the module. So you can't really define a module purely in terms of a commutativity condition. You need some sort of associativity condition. which is given by this nth product thing. Well, yeah, I'm not sure if that cleared things up or not, but. Okay, so I want to construct this example, or at least start doing it. So don't ask me why, but we want to take the direct sum of all of these modules for H, where the mu takes integer values, sum them all together, and somehow construct a vertex algebra structure on this sum. You could ask, why do I only want to take integer values of mu? I mean, you could just take my word for it that that's what we want to do, but it'll turn out that in a sense that's the only kind of thing you can do. If you tried to take a more general sum, you'd get into trouble. So a mental image of this algebra is kind of as follows. Okay. So this here in the middle was just a copy of H from last time. So the first thing, H already is a vertex algebra. So the thing with a vertex algebra is we already know it's going to have a state field correspondence. So to every element, there's going to be an associated field. So let's start by saying, well, what should be the field associated to 1, right? Or more generally, let's take one of these highest weight vectors, mu. And let me introduce a notation. Let me call this thing gamma mu. So already at the outset, I'm going to make an assumption, which is that in this vertex algebra, the translation operator T is going to be given by this operator L minus 1, which we already had. So remember, in H itself, T was given by L minus 1. We also have L minus 1 acting on the modules H mu. And so I'm going to assume that T is going to coincide with L minus 1 throughout the whole vertex algebra. Well, if that's the case, then we can just compute, and it's an easy computation, to show that T acting on this highest weight vector mu is actually mu times H minus 1 mu. Okay, fair enough. So then if you go back to the level of fields, this gives us a differential equation satisfied by this field gamma. Maybe to lessen confusion here, I'll put with round brackets. But for the case of H, it coincides with or without brackets. This means that the derivative of gamma must be equal to mu times normally ordered product of H with gamma. So if you were very bold, or a physicist, you'd just say, well, that means right? This is a simple differential equation, saying if you differentiate this field gamma, you get back gamma multiplied by H. So gamma must be exponential of mu times the integral of this field H. Except, well, it wasn't quite the product, it was the normally ordered product. So let's just put a normally ordered product here. Oh, and I suppose, I mean, there's a one parameter family of solutions, so really there should be some constant C, right? Well, so the amazing thing is this turns out to be surprisingly close to the truth. So the way we'll interpret this is, well, it's this constant C exponential mu sum, oh, I hate writing all this out, minus n over minus n, where n is over less than 0, exponential mu sum greater than 0. And the only term I forgot so far was the h0 times e to the minus 1, right? And the integral of that's going to be a log. Then exponential of the log is just z. It was multiplied by mu, so we get z to the mu h0. Okay? So just to, I mean, why is this equal to this? I mean, somehow the idea is you take this integral, and what does normally ordering mean? It means you take all the positive modes and you move them to the right, and you move all the negative modes to the left. So yeah?
Regarding uniqueness, there's a couple of assumptions here. Two of them are, so the second one is you can multiply this guy by anything that is central and that depends on z, and it will still satisfy. Well, I'm sorry, that doesn't depend on z.
I mean, I'm going to do it properly now.
Let's see. Okay, so that one I believe that it's doable. But the first one is this assumption on t being n minus 1.
Yeah.
If you remove this, you get a differential equation that has more solutions than the one that you have on the first line.
Presumably.
And this is always an itchy point when you give this lecture, and I don't know the answer to that. Is it? I believe when I took this class, it was wrong. Is it?
Whether there are other.
Whether there's a unique actual solution.
If you don't assume this here,
If you don't assume that and you just impose translation invariance on those vectors, you get a differential equation that is not the one that is on the first line. You get something that is that plus a multiple of gamma, I think. It could be multiplied by something, and there are no trivial solutions to this equation. So,
right?
and the question is, are those vertex algebras isomorphic or not? When I took this class, I was told they are isomorphic, and I never understood this proof. Whenever I give this class, I reach this point, and I don't know what the proof is.
Yeah, I mean, well, I certainly wasn't going to claim this, or much less prove it, so I don't know. Exercise. No, but really, I mean, very explicitly what I'm doing here is assuming, I mean, that this vertex algebra is going to be what they call conformal, which in particular means that the translation operator is given by this L-1 operator. So we were just talking about what could happen if you don't assume this And yeah, I'm really not sure. Yeah, so as I say, this was kind of a physics level derivation. So a more rigorous derivation goes as follows. Basically take this as potential definition and basically prove that it's the only possibility. That's kind of the strategy. So to get to that point, I need to prove a couple of preliminary formulas. So firstly, so we know that H0 acting on mu is mu multiplying mu. And positive guys kill it. So that means, so we can write down the OPE. H is simply mu, right? All the higher order terms vanish. Very good. So now we lift this to the level of fields using state field correspondence. H of Z with gamma mu of W must be mu times gamma mu times delta function. Okay. So this is the great thing about this vertex algebra formalism, is that you can start with relations that are essentially trivial to check, and then since you can transport everything via this state field correspondence, you get relations which would be an absolute pain to check explicitly. Okay. Now you look at this relation, and you can take any coefficient of z and w, powers of z and w that you like, so you get infinitely many relations in this algebra. So for example, if I want to know how Hn commutes with this field, I get mu w to the n gamma mu w. And in particular, if I put n equals 0, then H0 is mu. W. Okay, what am I doing? Okay, so what's the use of this relation? This says, so H0, so how can I characterize 1 here, or in general mu? Like the H mu is precisely that part of V in which H0 acts by the constant mu, right? See here, H0 is 0, H0 is equal to 1, H0 is equal to 2, etc. This relation is saying that gamma mu is some formal power series with coefficients, all of which commute with H0 by giving back this number mu. Consequence, gamma mu must shift you mu steps in this picture, okay? Or in other words, the field gamma mu must send H beta to H beta plus mu. That's what I'm trying to say. now to handle this kind of translating between different components of the space, let's introduce a little operator u from v to v. And all it does is send beta to beta plus 1. So it's kind of shift. And as you filter down in H, that kind of carries the corresponding vector to the corresponding vector. Another way of saying that is that U should be characterized by this condition and saying that it commutes with all of the non-zero modes of H. Okay. Very good. So now consider gamma mu, z I guess. And what we do, we think that it's going to equal that over there. So what we'll do is we'll take the two parts and multiply them on either side of gamma. Well, multiply by the inverse. So x mu sum in greater than 0 hn. So this is now some field which is sending h beta to h beta plus mu. So let's go back to h beta by multiplying by u to the minus mu. Okay. Plus n, yeah, just to, I mean, obviously standard convention is not to write the plus, right? But just to emphasize that it's the opposite of over there. Yeah, so I'm just multiplying by the inverses of the two things that you've got on that side. So so if gamma is equal to all of that stuff, then this expression should be basically constant, right? And that's what I want to prove. The point is, it basically is because, well, now by explicit computation, this whole thing commutes with hn for all n not equal to 0. Yeah, so I still haven't got to that point. Yeah. Okay, so it's a bit of a complicated exercise. Okay. So now, it's kind of a standard fact and representation theory that in this module, if you have some operator which commutes with, so we have the subalgebra of, sorry, let me write some of this. So basically Schur's lemma says that any operator that commutes with the action of that subalgebra must be a constant. So the consequence is that this whole thing here must be just some polynomial, or some Laurent polynomial. Now, as Alberto pointed out, we saw that it really should equal some constant times a single power of z. That was kind of the intuition, right? In particular, so since we're acting on h beta, h0 acts on h beta by beta, so it should be some constant z to the mu beta, and the constant, well, is probably going to depend on mu and beta, so I'll call it c mu beta. Should actually equal, remember that I'm saying on h beta here. So how do we prove that? So I've already used that t was equal to L minus 1. So now let's consider this operator L0. So in particular, its action on mu is, so recall that by definition, this thing was half h0 squared plus sum n greater than 0 h minus n hn. This whole part vanishes, so it equals mu squared over 2 mu, okay? So just a bit of an aside, but an important one. So I have this operator L0 acting. Suppose I have some eigenvector of L0, and let me denote the eigenvalue by delta. So this is usually called conformal weight. This number, conformal weight, is kind of useful because if I have two vectors with well-defined conformal weight, then the conformal weight of all of their nth products is uniquely determined. So exercise. Okay? So we already saw this commutator formula. So the first part of the exercise is to deduce this form of it, and then to deduce that formula for conformal weights. Okay, so yeah, I've basically run out of time, so I'm kind of going too fast at this point. But kind of by analyzing conformal weight, so the conformal weight of beta is beta squared over 2. The conformal weight of its image, beta plus mu, is beta plus mu squared over 2. Since the operator that's mapping the first space to the other is this gamma mu, some nth product here maps beta to beta plus mu. And the only value that does that is where this subscript is correct, right, is this particular value. Now that comes multiplied by a particular value of particular power of z, which is z to the power of mu beta. So basically, wave my hands a bit, but basically that proves this fact, okay? I mean, that's not a great place to stop, but I'll basically stop there and continue next time.